Okay, so now we're going to work out the specifics of this problem we kind of brushed through here. So here's the picture. Given 2,400 feet of fence, find the dimensions that give the maximum area enclosed. So our task is to find the dimensions, find the values of x and y. So we're not done until we find those two values. So we'll talk about how the solution goes and the technique for making this happen. So what was one thing we needed? We need to have a function for what it is we're trying to maximize. We're trying to maximize the total area. Now the area of one of them is x times y, but we have 4 of them. This was specified by the design of the problem. And so the total area is given by 1, 2, 3, 4 times xy. For our work this semester, we need to have this being a function of a single variable. If you have multiple variables, you must get rid of one of them. It is similar, not the same thing, but it's similar to the differential count we did when we talked about related rates. So we need to get rid of one of these variables, and in order to do that, there must be some other piece of information given in the problem that allows us to eliminate one of the variables. In problems of this type, and this is very common, the given piece of information, in this case, is the total amount of fence available. So we know that if you add together all 1, 2, 3, 4, 5, 6, 7, 8, 9 of those lengths, the grand total must be 2,400 feet of fence. So we also have one, 2, 3, 4 x's plus 1, 2, 3, 4, 5 y's is 2,400. And we can solve for one of these variables and substitute into this equation. It doesn't matter which one you solve for. It's equivalent both ways. You'll get the same final result both ways. I'm going to go ahead and solve for y, since that's probably the most natural to most people. So I have 5y is equal to negative 4x plus 2,400. And so y is equal to negative 4/5 x plus 2,400 divided by 5. Oh golly, I should know that, but I'm going to resort 2,400 divided by 5 is 480. All right, so y is equal to this expression. And so we can substitute that into the area function. So the area function, and now we may write this. Notice here I just wrote area, but this is now area of x because everything here is a single variable. This emphasizes I've achieved a single variable. This is 4x times this expression, negative 4/5 x plus 480. And that works out to be negative 16/5 x squared plus, oh goodness, 480 times 4. I should have picked a nicer number. 1,920. So I just distributed this in to simplify that algebraically. Top times top is 16, so I have negative 16/5 times x squared, and then 4 times 480 is evidently 1,920 times x to the first. So a of x is here, all right? Now, we also need the interval over which this is defined. Now, earlier we talked about, theoretically, the smallest value of x is 0. The largest value of x. The largest value of x can be found. Here's the technique. This is the relationship statement. It is the relationship between x and y. The smallest value of x and the largest value of x. The smallest value of x could be 0 because that's a theoretical smallest value. To find the largest value of x, here's the technique. Let the other variable be 0. Let the other variable be 0 and solve for x. Let the other variable be 0. So in this equation, if we let the other variable be 0, this falls out. And so the maximum value if you let the other variable be 0, divide both sides by 4, x is 600. So the smallest value is a theoretical. As this gets longer and longer, this gets smaller and smaller, the limit value is 0. That's the smallest value. The largest value is found by going back to this relationship statement, let the other variable be 0, and back solve for x. That tells you what the value for x is for the largest. And so the interval we're defined on is 0 to 600. Now, find the derivative. Let's see, that's negative 32/5 x to the first, plus the derivative here is 1920. And we need to find the critical values. There are no type 2 critical values because this is a polynomial. The only one is a type 1 polynomial, and we find that by setting this equal to 0. So if you set this equal to 0 and back solve for x, what do we need to do? Subtract off the 1920, so we have negative 32/5 is equal to negative 1920. And so x is equal to, multiply both sides by 5, 30 seconds negative. It's negative 1920 times, multiply by the reciprocal, negative 5 over 32. And trusty calculator comes into play here. 1920 times 5 equals, divided by 32 equals, I have 300. 300 is in the interval of interest. Any value you achieve that is not in the interval of interest must be discarded. So the only three possible values, I'm going to run out of space here, the only three possible values are 300 and then the two endpoints. So we have set up the function, we have found the interval, we have found the critical values, and so now we evaluate the original area function. At 300, at 0, and at 600. So 0, well, I can do 0. This function here, it's the negative. So at 0, that would be 0 plus 0 is 0. A of 300, that's plug 300 into these two values. Negative 16/5 times 300 squared plus 1920 times 300, sorry about the small space, and that should give us a number. So I have negative 16 divided by 5 times 300 squared plus 1920 times 300, and that value is 280,000. Oh, sorry, 288,000. And then the last is area of 600. And that's negative 16 over 5 times 600 squared plus 1920 times 600. And if you work that out on your calculator, that actually works out to be 0 again. And so you choose the largest. The largest is here. All right? The largest is here. Now, what were we asked to find? We're asked to find the dimensions. Well, the x value is 300. The y value, I've erased the equation that had the y value in it. The y value comes from this equation. Let's see, we had 4x plus 5y is equal to 2400. That should allow us to solve for y, because we know the x is 300. So that's 1200. So this implies 5y is equal to 1200. And so that implies that y is equal to a number. That is 240. All right. So that's kind of lengthy, but that's the solution. It doesn't take nearly so long if you don't explain it while you're doing that.